Ever wonder how a piano's tuned? Let's make sense of it with science. Pressing a key on a baby grand triggers a chain reaction that involves some 35 different parts and ends with a small hammer hitting a string or strings and creating a note. The key to tuning a piano is a tuning fork. When tapped, the fork vibrates, producing an A note. Now the pitch of this A is called A440. That means to create it, a string must vibrate 440 times per second. That's also its frequency. Anyway, the tuner presses the corresponding A key on the piano, then listens to hear if the note matches the tuning forks. When it doesn't, a series of beats are heard. The beats signify the difference between the piano's and the tuning fork's frequencies. The farther apart they are, the more beats. The tuner either loosens or tightens the piano's string to change its frequency or pitch. As the piano's pitch gets more and more in tune, those beats slow down until finally the piano's A matches the tuning forks. And there are no beats at all, which means the central A is perfectly tuned. And the piano tuner only has 87 keys left before his job is done, which will be music to everyone's ears. So now you know. It all makes sense with science. This has been presented by Bayer Corporation's National Education Program, Making Science Make Sense.
Kids. All right, I am going to talk to you today a little bit about beats. So the first thing you want to do is you need to copy this into your notes. So get your notebook out and put it in your notes. A beat is a periodic variance in amplitude that occurs when two close frequencies constantly interfere with one another. Yeah, that's a lot of words, and you might go, yeah, I don't really understand that, but I'll explain it in a minute. There is an equation for it. It is the beat frequency is equal to the absolute value of just F1 minus F2, so they do two different frequencies. But going over this, here's what this means. So if you need to pause it and write it down, pause it and write it down, and then you can restart it and listen to me explain it, and then you can write some more notes. But when we say a periodic variance, that means it happens over and over and over again, so it happens periodically. Variance meaning it's going to vary, and then amplitude is talking about how big the wave is. If you're talking about a sound wave, that means it's going to get loud and then soft, loud and soft, loud and soft, loud and soft, loud and soft. So it'd be like loud, soft, loud, soft, loud, soft, like that. And it occurs when two frequencies constantly interfere with one another. Remember, waves always pass through, which is our interference. So far so good? Yes, yes, yes? Okay. I'll be back in a minute with a diagram to help explain this more. Bye, kids. Hi, kids. All right. I'm back. So we're talking about beats. So I have two waves here. If these are sound waves, they're not represented very well because I drew a transverse wave, but it's easier to see a transverse wave, so we'll talk about this one. I have two waves. They have slightly different wavelengths and therefore slightly different frequencies. You can see that this one is a high frequency, this one is a lower frequency. If they are both played at the same time, like if this were sound, if you looked, right here, I have a crest on top of a crest. So you would get what type of interference? That would be constructive interference. If you're talking about sound, that would be loud. Okay, and then later on, right about here, you have a trough on top of a crest, so it'd be loud. And then you get destructive interference, so it'd be soft. And then constructive interference, and then destructive interference, and then constructive interference, and then destructive and constructive and destructive and so on. So that if you played these two sounds, if they were sounds, again, sounds are longitudinal, you get the idea, that it'd go loud, soft, loud, soft, loud, soft, loud, soft, like that. It'd be wow, wow, wow. And that's exactly what I'm going to show you next. Bye, kids. Ah, kids. All right. So I have two tuning forks here. This tuning fork, as you can see, has a blob of clay on it. So it's out of tune. So it sounds like this. It's supposed to sound like this. Okay, so they are do different pitches. So pitch 1, pitch 2. Okay, this one has a lower pitch, which should make sense because the clay is going to add a little inertia, meaning it's going to be harder for it to go back and forth. If it's harder for it to go back and forth, it's going to have a smaller frequency because it's going to go back and forth less frequent. So lower pitch, higher pitch. You guys should have already watched the little video clip about tuning a piano, but this one is out of tune. So let's say I want to tune these. Well, here's what I would do if I wanted to see if it is in tune. I know that this one is in tune, so I would go, okay, I'm going to play this one. Then I'm going to play this one. You guys hear it? The whoa, 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 whoa. That's your beats. That's loud, soft, loud, 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 loud. So it's loud, soft, loud, soft, loud, soft, and so on. And if I use my kids. All right. I have two tuning forks here. And if you can see, this tuning fork has a blob of clay on it. So it's out of tune. It's supposed to sound like this. And instead of sounding like that, it sounds like this. So it is out of tune. You guys should have already watched the video about the tuning the piano, so you should already have kind of an idea about this. But I do want to talk about it a little more. This one has the one with the blob of clay has a lower pitch because, and that should make sense. The clay adds a little bit of inertia. More inertia means it's harder for the tines to go back and forth, back and forth, back and forth. If it's harder for them to go back and forth, then they're going to go back and forth less frequent. Therefore, it is going to have a lower frequency, which is why it sounds lower pitched than that one. Okay. I do want to show you something here. This is my iPad. If I hit this, okay, that's showing this. Pick on me talking, but that is showing just this pitch. It's getting quieter because the amplitude's going down. But if I hit them both, okay, you're going to hear beats. Everybody hear the beats? The whoa, 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 loud, soft, loud, soft, loud, soft, loud, soft, loud, soft. Okay. In fact, I can show you the beats using my iPad. If I do it again. You can see using this that the amplitude got big, small, big, small, big, small, big, small, big, small, big, small. Well, I know that my tuning fork is out of tune, so I need to tune it. So I'm going to take some of the clay off. If I take some of the clay off, do it again. Okay, and you can see, you can hear that the pitch is you're still getting the beats. Wow, 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 wow. And if I show you using the iPad, you can see that you're still getting beats. You're still getting the loud, soft, loud, soft, loud, soft, loud, soft, loud, soft. So I know I'm not in tune. So I need to tune it again. Whoa, 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 whoa. Again, it's getting better. You can see that the beats are happening less frequently, so therefore my beat frequency is going down. Therefore, I'm getting closer to having my tuning fork in tune. Now, if I add just a little bit, you can hear the loud, soft, loud, soft, loud, soft. So I'm getting really close. In fact, if I go even more, so now I just have a teeny tiny bit on there. can see that it's happening almost perfectly in tune, but you're still getting the loud soft. Where now if I have it so it is in tune, there are no beats. You can see it was getting smaller because the amplitude's going down, but there are no beats anymore. Therefore, my instrument is in tune. So that when you tune a musical instrument, really what you're doing is you're trying to listen for beats. If you hear beats, that means it's not in tune, so you have to tune it a little bit until you hear no beats, and then you're in tune. Bye, kids. Hi, kids. All right, one last thing. Let's do a problem using beat frequencies. So let's say that, like we just did with our tuning forks, you heard 3 beats per second. So loud, soft, loud, soft, loud, soft, loud, soft. That happened 3 times every second. If one tuning fork was 320 hertz, what could the frequency of the other one be? Well, if you want to pause it and figure it out, otherwise I'll work it with you guys right now. But we're using our really complicated formula of this. So that if this is 3 hertz, so if this is 3 hertz, and let's say this is 320, well, that could be 3 less or 3 more. So it could be 317 hertz or 323 hertz. Cool. Physics is everywhere, even tuning musical instruments. Bye, kids.